So we're now going to start learning about special relativity. In order to do this, we'll start by looking at the Galilean transformations. Now, the Galilean transformations aren't the relativistic transformations, but they're a little bit easier to understand. So for the relativistic case, we'll need to learn about the Lorentz transforms, but let's get our head around the Galilean transforms first before learning about the Lorentz transforms. So the Galilean transforms were thought to be very applicable to pretty much everything up until the start of the 20th century. And that's because until that time, nothing moved especially quickly. So now we have particle accelerators and things where particles can get relatively close to the speed of light, and so we do need to start thinking about relativistic corrections to these experiments. But back at the start of the 20th century, everything went relatively slowly, and so the Galilean transformations were pretty good at describing how to get from one reference frame to another. So the Galilean transforms describe how we get from one reference frame to another reference frame, which is moving with a constant velocity relative to that first reference frame. So let's consider two reference frames. We'll consider Joe and his reference frame. So we'll put Joe in a transparent glass box so that he can see what's going on, but he doesn't actually need to walk to move. We can pull the box along. And we'll put Mo in another transparent box, and we'll assume that Mo is moving with a speed u to the right as measured by Joe. Now at time 0 in both these reference frames, we'll let Mo and Joe be at the same position. So not entirely physically realistic, but let's just forget about that for now and put them at the same location at t equals 0. Now, as both Mo and Joe are travelling at constant speeds, or no speed, depending on whose reference frame, neither of them is going to experience a net external force. Newton's law tells us that. So they can't do experiments to tell if they're moving or not. So let's sketch down Joe's reference frame. So we will call Joe's reference frame the S reference frame. And here I've sketched his X and his Y axis. He does have a Z axis as well, but we're leaving this off the sketch because we don't want it to get overly complicated. Now we can also show Mo's reference frame. Let's let Mo's reference frame be called the S prime reference frame, and Mo is moving with a speed u to Joe's right. So we can show his reference frame like this. We'll let his x-axis be the x prime axis and his y-axis be the y prime axis. Now what we're going to do is consider point P with coordinates x, y and z at time t in Joe's reference frame. And what we want to do is work out, well, what are the coordinates in Mo's reference frame of the same point, which we'll call point P prime in Mo's frame. So P prime has coordinates x prime, y prime, z prime at time t prime in Mo's frame. So we'll start by considering, well, what's x prime? So looking at this figure, we can mark on the distance x as measured in Joe's reference frame. Now, in a time t, Mo's frame has moved a distance ut along Joe's axis. So we can mark that on our figure as well. And here is the length x prime. So by looking at this figure, we can see that x prime is equal to x minus ut. So this tells us how we transform the x coordinate in Joe's frame into the x prime coordinate in Mo's frame. Now we can do similar things for the y prime. So in the y direction, there is no relative movement. So initially Mo and Joe were at the same location. They agree on what is y and what is y prime. And so as there is no relative motion, this doesn't change at all through time. So we have y is equal to y prime for all times. Similarly for the z and z prime, we have z is equal to z prime as there is no relative movement in this direction. So if they initially agreed that some length was z and that's the same as z prime, then as there's no relative movement, this isn't going to change at all through time. So z is always equal to z prime. Now, in the 20th century, it wasn't thought to be possible for time to be measured differently in different frames. So it seemed fairly obvious that t was going to be equal to t prime. So to summarize, the Galilean transforms are a way to convert a coordinate system from one frame to another frame, which is moving with a constant velocity relative to that first frame in the x direction. So the Galilean transforms are given by the equations x prime is equal to x minus ut, y prime is equal to y, z prime is equal to z, and t prime is equal to t. So let's have a look at an example now of how we can use this to convert from one reference frame to another reference frame. So the question, Mo's frame moves with a constant speed u to the right as measured by Joe. At t equals 0, Mo and Joe are at the same location. At t equals 0, Joe throws a projectile. According to Joe, the location of the projectile can be described by P of t is equal to VTI plus VT minus a half AT squared J. How would Mo describe the position of the projectile in his frame? If V equals U, what would Mo see? Okay, so to answer this question, we can apply the Galilean transforms as Mo is moving with a constant speed in Joe's frame. So our Galilean transforms tell us that x is equal to x minus ut, y prime is equal to y, z prime is equal to z, and t prime is equal to t. So according to Joe, the x location of the projectile is equal to vt. And so according to Mo, we've got x prime is equal to x, which is vt, minus ut. So we can write this as v minus ut. Now in the y direction, Joe sees the y coordinate of the projectile as equal to vt minus a half at squared. In the y prime frame, Mo's frame, there is no change. So we've still got y prime is equal to vt minus a half at squared. There is no z coordinate here, so presumably in Joe's frame, the z coordinate in the k direction is just 0 and remains there. So the same will be true in Mo's frame, and there is no difference in how they measure time, so the times remain the same. Okay, so now we've got x prime and y prime, we can write what this will appear like to Mo. So we'll call it t prime because we're in Mo's frame now, which is the prime frame. So let's also call it p prime. And so we have got v minus u. Now as t and t prime are the same, let's write this as t prime. And then we've got plus, this is the same, and again we'll replace t with t prime just so that everything is in Mo's frame. So we've got vt prime minus a half at prime squared, and then that's times j, and this will be j prime, and here I left off the I prime. So now we've written down the equation of the motion in Mo's frame. Now it says if v equals u, what would Mo see? So if v equals u, well this term here is going to be 0. So we'll have p prime, t prime is equal to vt prime minus a half at prime squared j prime. And so you see there is now no x coordinate. So in this case, what Mo sees is the projectile going vertically up and then coming vertically down. So Mo sees okay, so physically how we could imagine ourselves being in Mo's frame is if we were on a skateboard and we threw a ball up and we watched it, it would look to us in our reference frame on the skateboard, like the ball was going up and down. Whereas in Joe's frame, who's somebody standing besides the skateboard watching the ball does have a component in the x direction.